Annenberg Media.
Additional funding provided by the people of Dow, the company that lets you do great things. The 8,000 scientists of the Eastman Kodak Company. The Exxon Education Foundation on behalf of Exxon scientists. And
look at any corner of our planet, and it looks like it's been there forever. But the Earth is dynamic. It's been continuously changing for 4.5 billion years. The Earth's chemicals have been mixed, separated, and deposited unevenly throughout the globe. The Earth's surface is different from its interior. Why? And what are the forces that redistribute the elements and minerals? Rare and valuable minerals can be found in a few widely scattered areas. Scarcity inspires a search for substitutes, and today, our advancing technology can find new, exotic uses for the most common of substances. Both our past and our future are rooted in the chemistry of Earth.
The American philosopher and historian Will Durant observed, civilization exists by geological consent. Think about that. Since everything that we use ultimately derives from the Earth, the geographical distribution of minerals and ores determines directly global economics, politics, patterns of trade. Here is a sample of stainless steel. An important component in it is the metal chromium. Chromium is also used in alloys that make hubcaps and jet engines. And where does chromium come from? From ores from deposits that are found mainly, as are those of platinum, as are diamonds, in South Africa or in the Soviet Union. Another strategic metal, tin, is found mainly in Southeast Asia. There is oil under Saudi Arabia. There is very little oil under Israel. How did valuable minerals come to be in one place and not another? Well, there is a lot that we don't know about this yet. We don't know why one part of the globe was chosen to be rich in chromium and not another. But we've learned a great deal about how nature concentrates minerals, how it does it on the floor of the ocean or on the top of land. We've learned about how ore deposits are formed, the underlying chemistry of this planet.
Here in the African Bush Belt, an area the size of New England, located in southern Africa, interesting chemistry has been at work. Just beneath the surface lies some of the world's richest deposits of platinum, rhodium, and chromium. A mineral is a naturally occurring substance with a characteristic chemical composition. When minerals are concentrated and are economically valuable, they're called ores. Because some places are rich with ores and minerals, like South Africa, and others are not, the fortunes of whole countries, of people and their governments, can rise and fall based on the wealth found in their natural treasuries. Since prehistoric times, we have recovered and then used a variety of minerals. How did our ancestors obtain the minerals and elements they needed from the earth? One of the early techniques used in this ancient tin mine in Cornwall, England, was to build large fires at the base of the rock cliffs. The intense heat cracked the rocks, exposing the tin ore, which was then mined. Today, we use dynamite and ammonium nitrate to blast rock away from ore-rich veins. But while we blast and drill and probe at the earth, whatever we are able to extract is limited by our technology, our needs at the time, and costs. How have the minerals and elements come to be located where they are? To find out, we must begin at the beginning, billions of years ago. Scientists believe that within the swirling dust of the primordial cloud, chemical reactions were occurring. Most of the elements and a variety of minerals were there. Some minerals were decomposing and others were forming. Gravity was drawing the planet together. Initially, the Earth was a homogeneous sphere. In time, because of the natural radioactivity of some of the elements deep within the Earth, the temperature rose, and iron, one of our most common elements, melted and sank to the center of the Earth. The Earth's core was forming. This was the beginning of differentiation. Different rocks and minerals began emerging from the single homogeneous sphere. Lighter, molten materials floated up to the surface, where they cooled to form a primitive crust. The Earth was becoming a layered planet, with a dense iron core in the center. Just above it, the mantle, which is composed of dense silicates, and a crust of lighter rocks and minerals. The whole Earth itself is rich with iron and oxygen, silicon and magnesium, and minor amounts of other elements. But we can only conveniently obtain the elements which are abundant in the crust. Generally, the abundances in the crust are different from the whole Earth, as this graph shows. Notice, only about 6% of the Earth's iron is in the crust, where we can mine it. The rest is at the Earth's core. On the other hand, there are large numbers of combined oxygen, silicon, and aluminum in the crust. But minerals aren't evenly distributed across the Earth. In a few scattered places, rare and valuable elements have been concentrated. How? Ore deposits form in three basic ways. One way is by the crystallization of magma, molten rock, in huge chambers beneath the Earth's crust. The magma rises and comes in contact with cooler rock near the surface. Dr. Philip Candela.
It loses heat to the surrounding cold rock, and therefore it begins to crystallize. Now, when this molten rock begins to crystallize in the subterranean chamber that we call a magma chamber, there's not just one chemical substance crystallizing, but sometimes 5 to 10 different chemical substances are crystallizing out of this molten rock.
Scientists believe that magma originates within the mantle itself. When conditions are right, the solidifying rocks can contain elements like chromium and platinum. This must have been the case in the Bushveld of South Africa, where the ore deposits formed are both profitable and internationally strategic. The second way which mineral ore deposits form is through the action of superheated water. Deposits of tin, lead, and zinc minerals usually originate this way.
As this hot water is rising, it dissolves metals and can dissolve sulfur from the surrounding rock. And as this water rises to cooler levels within the Earth's crust, it loses heat to the surrounding rock. Also, this rising fluid can boil. The metal and sulfur dissolved in the water can combine to form sulfide minerals. These sulfide minerals may plate themselves along the walls of a fracture and form a mineral vein. For example, here we have a mineral vein. This is a granitic type of rock here that obviously had fractured. Hot rising fluids fill the fracture. Dissolved in that water was silicon dioxide, or which precipitated out from the solution to form crystals of quartz, which is some of the clear, glassy material within the vein. Also, the solution contained a metal called molybdenum, and also contained sulfur, and upon cooling, the molybdenum and sulfur united and precipitated from the solution along the walls of the vein to produce a vein which we now find in this rock of molybdenite, molybdenum disulfide, and silicon dioxide, or quartz.
Scientists think beneath these geysers and hot springs, ore deposits may be actively forming. These hydrothermal vents are also common on the ocean floor. This is a black smoker, a geyser at the bottom of the sea. While we have just recently been able to see them up close, they are already yielding new clues about how ore deposits form. It's a fascinating process. At the oceanic ridges running